This is the last lecture of Chapter 12, which deals with alkenes and alkynes. You may recall that alkenes have double bonds and alkynes have triple bonds. For this lecture, however, we will concentrate on the reactions of alkenes. The reaction type that we will consider is addition reactions. So we will consider the addition of hydrogen to alkenes. We'll consider the addition of HCl, hydrochloric acid, and HBr, hydrobromic acid, to alkenes. Notice again, I'm emphasizing addition because in these reactions you will notice that we'll be adding two molecules together to make the product. Another reaction that we'll look at is the reaction of water, H2O, to alkenes. Another type is the addition of bromine to alkenes. And lastly, we will look at polymerization, which is a process to make polymers. And of course, as we know, polymer is a material that's very important and useful in everyday life. So let us begin. Let us look first at the addition of hydrogen. Of course, as you know, hydrogen is H, two atoms of hydrogen, two hydrogen atoms bonded together to form the molecule hydrogen. So here's the double bond, and in the addition process, notice plus addition, one hydrogen atom will be added to one atom of the carbon double bond, and the other atom of hydrogen will be added to the other atom. Notice it's added to both carbons of the double bond. In the process, however, this double bond is transformed into a single bond. So the overall product is hydrogen is added to one carbon, the other hydrogen atom is added to the other carbon. This process is called hydrogenation. That's used a lot in industry to convert an unsaturated functionality, such as an alkene, to a saturated functionality. Another molecule that we'll look at is bromine. So here's bromine, and of course, as you know, bromine is Br and Br, two bromine atoms that are bonded together to form molecular bromine. As you can imagine, one bromine atom will add to one atom of the double bond, and the other bromine atom will add to the other atom of the double bond. In the process, this double bond is transformed into a single bond, and the bromine is added to the carbon by a single bond, and the other bromine is added to the carbon by a single bond. So these are called addition reaction, and this in particular is called the bromination reaction. Another one that we look at, let's go to the top one first, is HCl, which is H bonded to Cl. That is the molecule hydrochloric acid. As you can imagine, one hydrogen, the hydrogen will add to one atom of the double bond, and the other Cl will add to the other atom. This double bond will be transformed into a single bond, and we have H and Cl added to both carbons of the double bond. Notice they're not adding to the same carbon, but they're adding to both carbons of the double bond. Here's water. It can be written as H and OH. So once written this way, it becomes easy to visualize that the H here will add to that carbon, and the OH will add to that carbon. This double bond is transformed into a single bond, and the product is H and OH added to both carbons of the double bond, and this type reaction is called hydration. So let us look at a specific reaction now. The first one that we look at is hydrogenation. So here's a molecule, ethene, 2 carbons, 1, 2, and hydrogens bonded to both carbons of the ethene molecule. Hydrogen gas, as we explained earlier, hydrogen will be added to one atom of the double bond, or carbon of the double bond. The other hydrogen will be added to the other carbon of the double bond. The double bond will disappear to form a single bond. So this is unsaturated and this is saturated, and here is our saturated alkane. These reactions typically generate heat. So as you know from Gen Chem, they are called exothermic reactions. I should also point out that these reactions need a catalyst. You may remember that a catalyst is a reagent that's used in a reaction but not consumed, typically to make the reaction go faster or easier by lowering the activation barrier. So a specific reaction here is shown on this slide. So here is butene, 2-butene. Notice here it is an alkene because of this E, and the 2 indicates the position of that double bond. It's written as trans because the methyl groups are across from the double bond. In the reaction, however, which is an addition reaction, we're adding H2, which is H and H. So one H will be added to that carbon, and the other H will be added to this carbon in the presence of a catalyst. The catalyst here is palladium, but it can be platinum or nickel. The product is a saturated molecule. In this case, it is butane. Notice the A here for the alkane. Both carbons of the double bond, here they are, they're now CH2s. CH2s. Over here, it was just one hydrogen on each carbon of the double bond. If the molecule is the cis-butene, cis as written here, because both groups are on the same side, but it's still an alkene, we need to concentrate only on the functional group here, which is the carbon-carbon double bond. For an addition reaction of HH in the presence of a catalyst, we get the same molecule here. Notice the same molecule. Let's look at cyclohexene. Cyclohexene, here's the E to indicate that it is in fact a alkene with a double bond. Here's a double bond. Presence of hydrogen, addition reaction, catalyst will convert this double bond into a single bond. Notice this is written as your line angle structure. So there are no hydrogens written here. But we know that this carbon has two hydrogens because there are four bonds to a carbon, and this carbon has two hydrogens also. I'm emphasizing that because in the reactant this carbon only has one hydrogen, and this carbon also has one hydrogen. So here we have a product with two hydrogens added from our reactant through an addition reaction in the presence of a catalyst such as palladium. So this is an addition reaction converting cyclohexene into cyclohexane, which is our saturated hydrocarbon. Let us look at another type reaction, another addition reaction. This time we're adding bromine. And again, bromine is Br bonded to Br. Two atoms of bromine makes molecular bromine. These reactions are accomplished in the presence of a solvent, a non-reactive solvent, inert solvent, and you'll typically see it written on the arrow. Here is methylene chloride CH2Cl2, but it's a solvent. It's not a reactant. It's not part of the reaction. It is a solvent. The reactant are the alkene and bromine. Addition reaction. So first you'll have to carry out the analysis on the alkene. Here's the alkene, 2-butene, and here's the carbon with the double bond and the carbon with the double bond, the functional group. It's an addition reaction, so one bromine atom will add to one carbon and the other bromine atom will add to the other carbon. In the process, the double bond will be transformed into a single bond, and now we have two bromine atoms that are added to both carbons. Notice both carbons of the double bond to form a new product here, 2,3-dibromobutane. Let's look at this one, cyclohexene, the same molecule we had before. Here's the ene indicating the double bond. Here's the double bond. Notice I'm pointing your attention to the functional group, not over here, but always identify the functional group of the molecule. It is an alkene. Bromine, as we mentioned earlier, is Br bonded to Br. Here's our solvent. So when the reaction is done, this bromine is added here and the other one is added here as shown here. Again, this is the line angle representation, but don't forget there is also a hydrogen here and a hydrogen here because there are two hydrogens, one here and one hydrogen here. This reaction is very important in organic chemistry because bromine is a deep red color solution, and after the reaction is done, the product here is colorless. So if we have a molecule, an unknown molecule that has a double bond, if mixed with highly colored bromine, and if there's a reaction, it gives a colorless solution indicating the presence of a double bond. I think you will do an experiment like that in your lab. Let us turn our attention to another addition reaction. This one is the addition of HCl. So that's H and Cl. Notice again, here is our functional group right here. Carbon-carbon double bond. As you can imagine, the H will add to one carbon, and the Cl will add to the other carbon, and in the process this double bond is transformed into a single bond. So here's the H from this H here, here's the Cl from this Cl here, so that's called the addition of HCl, or the hydrochlorination of an alkene. This specific alkene is ethylene or ethene, double bond indicated from the E, goes to the saturated or the chloroethane molecule. Here's an alkene, another alkene. Here's a double bond. So here's where the reaction will take place. Remember again, a definition of functional group is a region of the molecule where a reaction will take place. Here is that region. Carbon-carbon double bond. Here's HBr. So we'll have H adding to one carbon and Br adding to the other carbon. So here's the H and here's the Br. The reason why it's written like this is because we're writing the line angle structure. So they're not necessarily indicating that they are on opposite sides, but just to indicate that they are on two different carbons. Let's turn our attention now to a process in organic chemistry we call a reaction mechanism. By definition, a reaction mechanism is a step-by-step description of a reaction in which arrows are used to show electron movement, to form new bonds, or to break bonds. Sounds like a lot, but let's break it down. As you know, if you mix two reactants together, they do not just magically form products. They go through steps before the products are actually formed. So that is the process that we call a reaction mechanism, and the description, which is a step-by-step description, is what we do, and we use arrows to indicate those steps. This gives you a little more detailed in terms of the arrows, but let me give you an example just to clarify. So looking at this reaction, so here is an alkene, ethene, because we have two CH2s and CH2 here, and we're mixing this with HCl, hydrochloric acid. So let's analyze hydrochloric acid from our knowledge in Gen Chem. Chlorine is very electronegative, as you know, and hydrogen is electropositive. This is a polar covalent bond right here. So the electrons in this polar covalent bond are attracted to the more electronegative atom here, chlorine. Hence we say it's partially negative. Remember that term delta, which means partial negative, and over here this hydrogen is partially positive, delta positive. Over here, the alkene, of course, as you know, is a double bond. A double bond here has two electrons in this sigma bond, or single bond here, and two electrons in another bond we call a pi bond. But the bottom line is it's a double bond with two pairs of electrons. Electrons are negative. So these two electrons indicated by that line, we use an arrow. Notice the head of the arrow is here. So these electrons bond to this hydrogen. Here's the hydrogen, and these two electrons form this bond. And in the process, since chlorine is electronegative, these electrons come over to the chlorine to give Cl negative and an extra pair of electrons. By the way, that should be red. I'll get that corrected when I post the PowerPoints. So this is one step. Remember, we say that a mechanism is a step-by-step description. This is the first step in how the reaction occurs. What's created here is called a carbocation. Why carbocation? Because it's positive, because we're taking electrons away from a molecule to make this bond. What's left behind at this carbon is a positive. Positive, of course, as you know in chemistry, is described as a cation. But since it's on a carbon, it's a carbocation. So this is an intermediate. It's not the product, but an intermediate of the reaction, generated from the first step. Let's look at the next step. In the next step of the reaction, this carbocation, which is positive, is attracted to 2 electrons from the chloride anion. So notice the arrow movement. It goes from the electrons to, notice the head of the arrow goes to the positive, because we're indicating electron movement to create this bond right here. So this is a new bond. Of course, as you know, or as you will recognize, this is the product. So this is the final step of the reaction. It's a 2-step mechanism. The first step involves the electrons forming a bond to the proton right over here, and the second step involves the chloride anion forming a bond to the cation, and this is the bond, and this is the product. So the overall reaction is this alkene reacts with HCl to give this as the product, but it's a 2-step reaction where these electrons react first to form this bond with the H, and in the next step this chloride reacts to form this bond to form the product. 2-step reaction, a mechanism or a step-by-step description of how the reaction occurs using arrows to indicate electron movement. Let us look at another example here, another way of writing it. So this is our butane. Here's our double bond right here. 2 electrons, negative, acid, H plus from HCl. Remember, we said this is partially positive and this is partially negative. So because this proton here, we can also write it as H plus. So the arrow moves to the H plus, or the electron moves to the H plus as indicated by the arrow to form here a carbocation, intermediate. Don't worry too much about the secondary. It is a carbocation intermediate, not the product, but a intermediate. In the next step, the chloride, 2 electrons, bond to the positive. Remember, electrons are negative, and here we have a carbocation which is positive. So here we form this bond, and that is our product. So that's the 2-step. Step number 1, as shown here, to form the carbocation, and step number 2 to form the product. So that's a mechanism. You will be asked to write mechanisms for reactions. They're typically 2-step mechanisms, just to make sure that you understand how reactions occur. Let's look at another reaction here. So this one is Another type alkene. Notice that this alkene here has a carbon that has one hydrogen and a methyl group, and this carbon has two hydrogens. So they are different carbons. So as a chemist and as a good observer, you can see that this hydrogen can add to this carbon or to that carbon. And likewise, this chlorine here, or the chloride, can add to that carbon or to that carbon. Bottom line is there are two possible products. Two possible products. So in one case, this hydrogen adds to this carbon to generate this product. In the other case, this hydrogen adds to this carbon to generate that product. Stated differently, this chlorine adds to this carbon to generate this product, and in the other case, this chlorine adds to this carbon here to generate another product. So two possibilities. In chemistry, it's very important after you do a reaction to determine which is the major product. So after you do this reaction, one of these products will be the major product and the other one will be the minor product. You will be asked to write the major product for a reaction. So we'll know how to deduce that in a second. But let's look at this reaction here, which is the same reaction as this, but just written using the line angle. So here's propene, same molecule here. Here's hydrochloric acid as written here. But notice we have the products written as line angle, and the other product over here written as the line angle, which is basically that. And this is that written differently. So you should be comfortable writing the different products using the line angle representation. But the question at hand is, how do we predict the major product? We have a rule that was discovered by a Russian chemist called Markovov. So the rule is known as Markovovs Rule. Let's state that and then we explain it. It states that the hydrogen of HX always adds to the carbon with the most hydrogen. And the X of HX, so it could be the chloride, adds to the carbon with the least number of hydrogens to give the major product. So let's apply that and then we come back and summarize it. So here is propene. So we'll have to look at both carbons of the double bond. This carbon has two hydrogens, 1, 2. So this carbon has two hydrogen. So it is the carbon with two hydrogen. The other carbon here has one hydrogen. So this is the carbon with just one hydrogen. So by comparison, this carbon has more hydrogens than this carbon. So the hydrogen, as stated by Markovov, will add to this carbon, and the X, as stated by Markovov, will add to that carbon to give the product. So let's analyze that using this reaction. So here is the H. It will add to this carbon because it has the most hydrogens, two hydrogens, and this chlorine will add to this carbon because it is the carbon that has the least hydrogen, one hydrogen, to give the product over here, which is the major organic product as defined by Markovov. You'll see that name quite a bit, Markovovs Rule. So once again, Markovovs Rule states that the hydrogen of HX will add to the carbon with the most hydrogens, and the X will add to the carbon of the double bond with the least number of hydrogens to generate the major product. You'll see in the book that these reactions are described as Regis selective because they select a particular carbon in the reactant to add to. Let us look at an example. So if you were asked to predict the major product, so in other words, let's look at the question. Give the line angle structure for the addition, notice addition reaction for each of the reactions given below. So this is the major product here. Here's a double bond. Here's one carbon off the double bond. Here's another carbon off the double bond. So therefore, this has just one hydrogen, and this carbon has none. So therefore, this is the carbon with the most hydrogens. Here is HCl, so we'd expect this H to add to that carbon, and this Cl to add to this carbon to give us the product. The product is shown on the next slide. Here is another example. Here's a double bond, and here's the carbons of the double bond, or here are the carbons of the double bond. As written, line angle, this has one hydrogen, so therefore this has more hydrogen, even though it's one, compared to this carbon which has none. So we'd expect this hydrogen to add here, and we'd expect this bromine to add over here to give the major product. So let's look and see what the major products are. As you can tell, the chlorine will add to the carbon with the least number of hydrogen based on Markovovs Rule, and the hydrogen will add to the carbon which has the most number of hydrogens, in this case just one, to give this as the product. Notice again, the line angle, we do not write the hydrogens in. Here's the same situation. Carbon of the double bond, no hydrogen. Carbon of the double bond, one hydrogen. Here's the hydrogen. Here's the bromine, or the X. The bromine will add to this carbon, and the hydrogen will add to this carbon to give this as the product. Notice again, no hydrogens written here because we're using the line angle representation. So you should be able to predict the product of these addition reactions using the Markovovs Rule to determine the major product. Let's turn our attention now to the addition of water, called hydration. For the addition of water, so as I stated earlier, we can write water as HOH. So using Markovovs Rule, notice we're still using Markovovs Rule here, the hydrogen will add to the carbon that has the most hydrogens, and the OH here, X, will add to the carbon with the least hydrogens. So let's analyze the alkene. In this case, it's ethene. So here's one carbon, two hydrogens. Here's the other carbon, two hydrogens. So they have the same number of hydrogens, which means that it does not make a difference here. So this hydrogen can add to that carbon, and this OH negative can add to this carbon to give that as the product. Let's look at this one, however, a little different. So this is the addition reaction of water. Notice we have here H plus, H sulfuric acid. It's a catalyst. So these reactions are carried out in the presence of a catalyst H plus. Remember, catalyst by definition is used but not consumed in the reaction. So the main reactant here is H2O. So let's analyze the double bond. So this carbon here has one hydrogen. This carbon here has two hydrogens. So now you know if you have HOH, this hydrogen will add to this carbon since it has two hydrogens, which are more than this carbon, which just has one. This OH will add to this carbon, and here's the product. So this OH adds to this carbon, and this hydrogen adds to this carbon here, and that is the major product as predicted using here Markovovs rule. Let's look at another example. Hydration, catalyst, HOH for our water, carbon after double bond, no hydrogen, carbon after double bond, two hydrogens. So you'd expect again this H to add here, and this OH to add over here, and here it is. So again, you should be able to predict the product for these hydration reactions using here, of course, Markovovs rule. Let us look at the mechanism for the addition of water. For the addition of water. What is the mechanism? Remember, the mechanism is a step-by-step reaction. The first step is, remember we mentioned the catalyst, sulfuric acid. In the first step, these electrons after double bond, it doesn't react with water because it is not acidic enough as with hydrochloric acid. So we put a catalyst in, H+, and it generates that carbocation, as you can see here. This carbocation has a positive right here. In the next step, here's water now. Of course, as you know, water is neutral, but it has a pair of electrons right here. These electrons can now bond to that carbon to make this bond right here. This arrow indicates that electron movement. So here we have this other intermediate, because oxygen, of course, as you know, has two bonds to it. Here we have three bonds, so we'll have to get rid of one of these hydrogens here, and here's how we get rid of it, using these two electrons to put that electron, those electrons onto oxygen, and here they are, to generate our neutral molecule, and here is the H plus that's left behind, and that is our catalyst. So this is the mechanism. This is a three-step mechanism for this reaction. Again, the first step is just the double bond, or the electrons of the double bond reacting with our catalyst to generate the carbocation. That's needed so the water molecule, which is neutral, using its electrons to bond to that carbocation to make a new bond. This is another intermediate because oxygen here takes two bonds, so we'll have to get rid of one, and we get rid of one by moving the electrons here onto the oxygen. Here it is, and here's our catalyst. So that is the mechanism for the addition of water to an alkene. So here are some examples. So here, looking at the same example we had before, methyl cyclohexene, here's our double bond, here is water, here's our catalyst. What is the product? The product, of course, is using the example we had before and Markovovs rule. Here's the carbon of the double bond, here's the other carbon of the double bond. This has one hydrogen, this has none, so you'd expect the H to go here and the OH to go here to give the product. Same thing here, one hydrogen, none. So using the same example, you should be able to predict the product. The next slide has the product, so let's see what you should have gotten. So over here, the OH adds to this carbon since it has the least number of hydrogens, and the H adds to this carbon since it just has one hydrogen, which is shown here to give the CH2. So this is the product. Notice again, the reaction takes place at the functional group, and here is where we have the product that's different from the reactant. Same concept here. Here's the functional group, here's our reactant, and we adding OH and H across that double bond to get a new product shown here. So you should be able to predict the product of an hydration reaction in the presence of a catalyst. Let us look here now at polymerization. As we said earlier, polymers are used in everyday life, and by definition, it's a Greek word, polymer, meaning many. Poly, of course, you know, is many, and mers here means units. So it's many units. So what we have here is a monomer, just one monomer or one unit, and through the process of polymerization we have many units now bonded together to form a polymer. What you'll discover in the next slide is the monomer is actually an alkene. So let's look at that. So here is an alkene. Here's the alkene. In the presence of an acid, we generate a carbocation. However, if we have a lot of alkenes present, alkene molecule present, these electrons here can react with that carbocation to form a new bond. Here's a new bond from these electrons coming in. What you'll discover is a carbocation is generated again. So the same process can happen again. So these electrons here can react to form another bond. So it just keeps going. That's why we have N. So N here indicates the number of mers or units. And of course this is an intermediate because it's a positive charge. If we should lose a proton, we get the neutral polymer, which is shown here. So this is an example of a polymer. Here's another example. This one we use in propene, which we've seen before. Through the process of polymerization, here's what we get. Really a long chain. So we can write it, instead of keep going and going, we can write it like this with N in a bracket to indicate the repeating units. So here's the repeating unit because it's the same here and it's the same here. So we just put the repeating units and put N. Using line angle structure, we get that. So this is a polymer known as polypropylene. Polypropylene. This is a polymer that's of importance. It's called a low density polymer, as we can see here, and it has properties soft, a melting point here, and it's used in industry. So you can see it can be molded into squeezable drugs and bottles. So the water bottles, some of the water bottles that we have are made from that polymer. Another example of its use is shown here, and this is a type saran wrap. So you can see here how it's made. So here we have air coming in, here's a polymer, and we can put air into it so we can have it rolled into a sheet, and that's what's produced as the saran wrap sheet, because it's from the polymer here. So in conclusion, let us look at some of the monomers that form very usable polymer. So here's one monomer, ethylene, and this is used as a break-resistant polymer. Here's one that we should be familiar with, is this monomer, vinyl chloride, and it's used in polyvinyl chloride. You may recognize that as construction tubing or construction piping, PVC piping. It's made from this monomer through the process of polymerization to form that polymer. And of course, here's just another list. Here's another important one. Tetrafluoroethylene, and it's used in, after it's polymerized, it's called Teflon. And of course, as you know, Teflon is used as a surface in our cooking containers, which is highly resistant for non-sticking surface. So you can go through this list and look at others for your information and for practical reasons. But that is the importance of polymerization. I think this is the end. Yes, so this is the end of chapter 12. So once again, take your time, read through the chapter, go through these PowerPoints, take your time, go through it. You may have to pause at different points so you can practice and predict the major products or the products for these reactions. And of course, I will put out a tutorial set over the weekend so you can carry out some more practice with that. So continue to read in your text, and I will post the video shortly along with the PowerPoints so you can follow along. So continue to study hard and get ready for our next quiz. Okay?